with something technical on the agenda. Yeah. So for today, I wanted to talk about. First, I want to do a small thing in that exercise we had yesterday, and that thing was to calculate the velocity in every position in the tubing. Okay, we have already pressure and we have temperature, so we have everything we need to calculate the the local volume rate, and then we can calculate the velocity. And that's really like an initiation to because when you work with multi-phase flow, you have to do that process for every point. You will see that it's exactly the same concept, but we have to. For multi-phase, there is no escape. We have to do it. So we have to discretize and we have to calculate velocities, and there is not only gas, but you have also liquid and gas. Okay, both. And you have to calculate that local velocity. You will see that that gives you the pressure drop, and you have to calculate properties, so it's a big process. So I think to do it is a good exercise for to as a preparation for multiphase. And then we're going to move to this mystical component in the production system called the choke, and we are going to see first some how the choke looks like, some what's happening inside the choke, what considerations we have to have when dealing with choke, and at the end, the last, we're going to see a model for dry gas through a choke. Okay, and next week, if we have time, we're going to cover slightly a model for multiphase. Okay, but let's see if we have time. I think if you learn for gas, if you understand it for gas, it's basically the same, but different equations for multiphase. So I think there is a really good value, high value of learning it for gas. So we're going to make now. So now it's like a class exercise, and I hope that you can work with me, or we give some time and you work also. So I want to calculate. The objective is to calculate the velocity of the gas at any position, or the velocity of the gas versus TBD for the example that we made yesterday. Okay, and I have sent you a file where we have, it's exactly the same file that we did yesterday, that you have TBD, okay, in meters, and we have 0 all the way to 2834, I think was the number, the length of the tubing. It's going to be dangerous to have the light like that. And then we had the temperature, and that went from, I think was something like 3, that was in Kelvin, okay? And I think it went something from 360, right? 360 to 380 in linearly. And then at the end of yesterday, we calculated pressure in bar. Yeah, and that went from 40 all the way to, I think was something like 85 bar. Okay, and that's very important. We want to see how the pressure is changing along the tubing. And now what I suggest is say, okay, now let's create, or now let's compute the velocity at each position in the tubing. Okay, and I told you that there is an equation that we can use to convert from a, so we say the Q of the gas at standard conditions. Okay, remember the bar indicates that is at standard conditions. It times the Bg at a particular pressure and temperature. Okay, that gives you the Q at local conditions. Okay, this is Q volume rate at local conditions. Yes, correct? Yes. Okay. And remember, this Bg has a lot of things inside, but has also the deviation factor, this set. Okay. So what I suggest is create one more column for each point, pressure, temperature, to calculate set, the deviation factor. Okay, and for that we are going to use our equation C fact standing. Okay, using this pressure and this temperature and the properties of the gas. And after we have it, then we can calculate Bg at each particular point in the tubing. And after that, we can compute Qg, right? And then how do we calculate velocity? We have the local volume rate, and then we have, just to calculate the velocity of the gas, we just say that's velocity, okay? That's not volume. Maybe let's use just u, okay? Velocity of gas is going to be equal to qg divided by just the cross section area of the tubing, right? Okay, so here we have qg over p v squared times width. Okay, and at the end, that's what we are going to get, ug. Yes, so that's the process. Let's do it, and I will do it, and give you enough time. And so let's see if we can do it together. So as a file, I took away all the CT, what we have done yesterday. Now we are focusing, after we have pressure and temperature, we want to calculate what is the velocity in every point in the tube. Okay, you see I have exactly those columns, C, BG, QG, and V local. So C, remember we have this function called C factor standing, user defined. And here we need P, the pressure. The temperature here was something tricky. Okay, remember that this function it needs the temperature in Celsius, and we have it in Kelvin. So we have to put here minus 273.15. Specific gravity of the gas, I have it here, 4. Then the unit, because that's SI unit. And we got a number. The pressure is relatively low, so we expect that it will be relatively close to 1. We bring it down, and we got from 96 to 95. Now we have the BG. That's the function that we already used 3 days ago. So we click Alt F11 to see how the function look like. BG, okay, and it requires the pressure, the temperature, the deviation factor, and then the unit. Okay, it needs pressure in bar or psi, temperature in Fahrenheit or Celsius, and the deviation factor. And the unit I have to use 2 because I'm working with metric. Yes? So I come here and I call that function Bg, pressure, temperature, and remember height is in Celsius, so I have to again to subtract 273, the deviation factor, and the unit is 2. Okay. It gives me that basically that means that the volume at the surface is 0. The ratio between the volume at any pressure and temperature divided by the volume at standard conditions, the ratio is 0.015. Okay, and then to calculate the local rate, I just multiply the rate in standard conditions, block it, okay, because that's constant. Remember, every section of the tubing is transporting the same rate, okay, times the Bg, and that gives me a smaller rate, which is okay. Remember that this gas, when it goes to the surface, it starts to occupy more and more volume. So logically, you have to say, if I now see in the tubing when it's under high pressure, then I should have a lower volume than this one, okay, than 1 to the 6. And then comes the final step, which is I take this rate and divide it by the cross-section area of the tubing. Okay. It's here, and I block that area because it's constant for every section, and I got something strange. Oh, yeah, because that's cubic meter per day, so I have to change from day to seconds, okay? Because velocity, I express it in seconds. So let's see. This one is meters per day, and one day is 24 times 360,000 seconds. Okay, so I have to divide by this number. Yes, and then I divide here by 24 times 3600. I got 52 all the way to 25. Okay, so now please do it on your computer, and and then we resume. I'm going to plot it versus depth to see how it looks like, but just check, just to check that I did it properly. Okay, so density, I'm going to use that function that I call density of the gas, and density requires pressure in bar. Okay, temperature in Celsius, so the temperature I have again to subtract 273.15, have it in Celsius. Deviation factor, okay, and then the specific gravity of the gas, I block it, and that gives me actually 22, a density of 22. Let's check if everything looks fine. Okay, 22, and all the way down is 45. Okay, the density of the gas. Let me check that I am doing things correctly. Pressure, temperature is B13, deviation factor is D13, and B6, that's this number here, B6. Okay, so that seems to be correct. Now I use erosional velocity. Also, I have programmed it for you. If you go Alt F11 once more, and now you go, I think I put it in auxiliaries. Okay, so you have two functions. One of them is V erosional, and that's exactly that expression that I showed you before, 100 divided by the density, but I'm also doing the unit conversion inside, so it will give me right away in meter per second. Okay, so you have to use this V erosional using the density. V erosional, density of the gas, and then going down. Okay, so I leave also some time. I leave also some time that you can do it. Okay, so let's see that function. It's called STOG. Okay, interfacial tension, sigma. Okay, so I call it here STOG, and that requires the density of the liquid, and the density of the liquid I gave it here, 897. I block it. We are assuming that doesn't change too much with pressure. And then the density of the gas here, and enter. Okay, there is some variation, but not much. From 29, that's dyne per centimeter, to 26. Then finally, I can call this Turner equation. Turner, it's here, it's called B Turner. Okay, so I call it B Turner. And the density of the liquid is here. I block it. That will be constant for everyone. The density of the gas, I have it here that I calculated from before, and the interfacial tension. Okay, and then I drag it down. Yes, so let me just copy that table so you have it in the notes. Okay, so this one was the function, that's a VBA function called STOG, and that depends on the density of the liquid. Well, density of the liquid and density of the gas. Okay, so here is taking this number, and here is taking this number. Okay, and this one is also a BBA function called B Turner that depends on the density of the liquid, density of the gas, and this interfacial tension. Okay, and the interfacial tension that comes from this column. Okay, so now let's plot how that looks like. Okay, and that's the graph I got. Okay, now I ask you, are we going to have problems with this well or not in terms of liquid loading? Not really. We are really the velocity is here, and we have to have this velocity. So really, we have a very good margin for liquid loading. Okay. Yes, maybe with time the rate is going to go down, so maybe you will come closer. But really, there is no. I have no problem. Looks like. Okay. Yep. Clear. Yes. Okay, so that was another application. We already calculated the pressure along the tubing, and we wanted to see what to do with this pressure. Okay, what can we help it? So I told you one is to make diagnostic to see where I might have problems in the well, and one thing is also to verify these conditions on the erosion and on the liquid load. Okay, and like I told you, the most critical point is for liquid loading is here. That's where the velocity is the actually the lowest. Okay, and for erosion usually it's at the wellhead. Okay. What are we doing then to make the other conditions to meet the diameter of the pipe? Yeah, you have to reduce the rate basically of the well. Okay, if you want to use the same well, you have to reduce the rate. Mhm. Also, some people say that this API criteria is too conservative because remember this equation came from API. Okay, and they say it's too conservative, so they recommend using another C which is higher. Okay, so maybe if you relax the C, you might be able to produce it. But that's at least what using the API equation, that's what it gives us. Ready? We're not changing the pipe. No, well, it's a big job. Change the pipe, and also it's going to give you less production. Well, yeah, but already we have, this is like I think this is like 6-inch pipe. That's a very very big pipe. Okay, so you have either another option that you might do is to increase the pressure. Okay, if you increase the pressure, this size of tubing is usually used for subsea wells. Okay, for subsea system where each well has to produce a lot. And these systems they don't produce with a wellhead pressure of 40 bar. Okay, they produce at a much higher pressure. And if the pressure is higher, then the rate is lower, and if the rate is lower, the velocity is lower. Okay, so probably you won't be violating. Okay. Yes.
So it's which type of the IP is it onshore?
Offshore usually. You want every well in offshore really is very expensive, so you want each well to count, okay, to produce a lot, the maximum that it can produce. Okay, so usually you have, in onshore you can drill many wells and all of them can be small and they might be relatively cheap to drill. But if you are offshore, each well is really a big investment. So each well is like is your little baby. You want to keep it, the best to do the best with each well. Okay, so each offshore gas well really produce a lot compared to an onshore. I think the I'm not sure, I cannot give you a number, but like um, offshore offshore gas wells, okay, the typical production is around like 3 e to the 6 standard cubic meter per day, or that's something like, I think it's like 30 million m mmcf per day. Okay, while for an onshore it might be a third of that. Okay, a big onshore gas well might be a third of that. Okay, so that for that we really need to go for a very big, and this is a very big tubing. This 6 inch is a very big tubing. Clear? Are we ready to go now to some theory on the choke? Yes? Okay, now we are done with exercise. Let's go for choke. Okay? So some discussion, like I told you, choke, I'm going to use the example of gas to teach some concepts, but really the choke usually is operating with multi-phase flow. Okay? So let's talk about production choke. Okay? And production choke, remember we had basically two types. And one of them was this that is called also positive, or also referred to as beam choke. And you had another type which was adjustable. Okay, and the beam choke is like a 90-degree arrangement where you have a pipe, okay, and then you have a bend in 90 degrees, and you have here like an opening that you can just unscrew, or you can just use a flange, okay, and you can actually come here and change. You have like a recess, okay, so that's part of the piece, maybe something like this, okay, and you come and you open here and you substitute this part for as something that you can screw, okay, it's like something like this, something like that, okay? So the fluid comes on this direction and enters into this beam and then goes out. Yes? And then if you need to change it, you just take out this cover, change. Of course, you have to close the well, okay? But you have to change this cover, unscrew, take the red part, and put a different diameter. And the sizes usually typically are something like 1/8 of an inch. Of that, that's of the length is typically around 6 inch. Okay, it might be shorter, but the space that you have available is like 6 inch. That's standard. And the sizes, this is the orifice size. Okay, and that means the orifice, this small opening here, and it's from 1/8, it goes all the way usually to 2 inch. Okay, and it goes not in any size, but it has certain size. It goes in intervals or in steps of 1/64 inch. Okay, so you have 1/8 plus 1/64 and so forth. Yep. So this will be the first one will be 8/64, right? That gives you 1/8, and the other one will be how much? 32/64. Yes, of an inch. And then you can use anything in between. And the point is that remember the intersection. Okay, if we had I'm not sure if you already forgot, but we had something called WPR, okay, wellhead performance relationship, and we had a P separator, okay, and we had a rate that we wanted to produce, okay, and we had this delta P choke, okay. But with depletion, and we'll see if next week we can make an exercise on that, with depletion the WPR goes down, down, so you have every time step you have to open the choke, okay. And if you have this type of system, what you have to do is you have to go physically and take out the bean, okay, and use one of a bigger hole, okay, of a bigger size. Yeah. And then we had, I told you we had the adjustable type, okay, that the adjustable was, let's see if I can make it pretty, I'm not sure. Okay, that's called a needle choke. Okay, I pull it up and down to regulate the opening that I have in between. I also have different types. I have also something called rotary disc that I'm going to show you now, a figure that I cannot, make a drawing, so I just take a figure from a book. Okay, that's a positive beam. Let me just, that looks much nicer than what I did. Okay, and that's the part that you replace, this part here. And let's go for the rotary type. This one we can close. Okay, that's the rotary disc. Basically, these are two discs, and this is some is still used. It's maybe not so used anymore, but it basically is two discs that are, one next to the other or one after the other, and they have the holes in the same place. But you can rotate one disc, and the other disc stays in the same position. So when it's exactly aligned, you have very low pressure drop. But when you start to disalign them, you start to increase and increase and increase the pressure drop. Okay. So that's your here you are fully choked. Okay. I think I had a picture of that someplace, but yeah, I think maybe let me find. I think I have it. I know where to find it. Okay, we had quite a few of. Okay, that's the choke. So the fluid comes through here and then exits through here. Okay, and here you have the two discs, one here and one here. Okay, and I think I have even a video. So that actually is taken from our university. We have one of these. And you can see the choke, that's the fixed part. And here you see the holes, they are aligned. Okay, and here they were not aligned. Okay, and you have one part that when you rotate, you actually move one with respect to the other. Okay, so I'm going to maybe put that picture, looks nice. That's a real production choke for high pressure, 10,000 psi. Very high pressure, so that's why you have such thick walls. Maybe put it here, let's see. And then you have the workhorse that we explained the first class, that was the cage. Okay, that is actually what people are using now, the cage choke. Okay, this one that you had one cylindrical part with holes that you take it up and then it's exposed, and then the jets impinge in front of each other, and then you have less erosion. Okay, that's what people are migrating to. This one apparently has a lot of problems related with fatigue. Okay, exactly, the point gets broken because you start having oscillations and it breaks. This one also some issues with it, and then finally people are converging to cage. Okay, but in this analysis, what we're going to make is we're going to focus on the bean choke geometry. Okay, because that's very easy to analyze, see it physically, the bean choke. So now let's say focusing on the bean choke geometry. Why? Because all of the others, they are a bit more complex. Okay, the flow, you don't know exactly how it goes. So we are going to focus and say we have the following. We have an area A1, then we have an area A2, and then we have area A3, which is usually equal to A1. Okay. So what happens with the fluid when it goes through the choke? We're going to paint it like that. In this contraction, this is a very abrupt contraction, and actually the fluid at this point, it doesn't occupy the whole space of area 2, but it forms something called, it's a Latin name, very fancy, that you heard in fluid dynamics, vena contracta, yes? Or like a Venturi type, yes. Okay, and then it starts and opens again. And you have all around, you have here some eddies, some turbulence, okay? But here in this point where you have the minimum, that's called the vena contracta. And you can have all kind of geometries, but people say, well, in principle, okay, fundamentally every choke is like that. You have a reduction and then you have an expansion. Okay, so that's why most of the choke models, they're based on this abstraction. Okay, even though the geometry might be very different, but most of the choke models, they're based on this abstraction of the choke. So let's look at the function of the choke. Okay, what is the main function of the choke? Okay, it's just to drop the pressure. Okay, and by to drop the pressure is like a different way to say you want to dissipate a lot of energy in a very short place. Okay, in a concentrated, okay, and that means to reduce the pressure, and you don't want to go up. Okay, you have some other arrangement, remember, that we use for metering, something like this. You remember that, an orifice, and the idea is that you drop the pressure locally, but then it has to recover. Okay, but here we make that very very long, such that the recovery is very very low. Okay, you don't recover much through the choke after that. Okay, so that's the intention here. You almost recover 100%. That's done for metering. You don't want to drop pressure. Okay, that's a orifice for metering. Okay, but we have a lot of, like we say, we know we want to say we get with this, and this is just to control production. Okay, we want to control production. Let's say the natural equilibrium rate would be much higher, and we want just to restrict it for some reason, erosion, all kind of reason. My separator cannot take that amount of gas, that amount of liquid, etc. That's the main function of the choke, to control production. But we get a lot of undesired consequences. Okay, and one of the consequences is that, remember, the when the pressure when the pressure drops, then you get, if you are talking about a liquid, you get gas vaporization, right? Because the pressure is dropping. So you get, in oil, you get gas vaporization. Okay, if gas, you get liquid condensation. Okay, you know, liquid start to liquid condensation. Okay, then after that you get the pressure drops. Okay, and then you cause these issues with the fluids. Then you have erosion. Okay, due to the high velocities in the choke. Okay, especially in this vena contracta, you get a very high velocity, and then you cause a lot of erosion. Let me see if I have an image. I think I pulled an image. No. Okay, I can pull maybe during the break. I can put an image of the erosion. Okay, and then you can have cooling. Okay, and that's especially particularly for gas. Okay, so why do you get to cooling? How do you call this effect? That when you drop the pressure very much in a gas, how do you call this effect? My friends, mechanical engineers or chemical engineers? No one here? No friend? Is this Joule Thomson? Okay, Joule Thomson effect. Joule Thomson Thomson effect. Okay, and so let's take. I think that's worth discussing a bit, and then we are going to take a break. Okay. So let's see, this is the phase diagram of methane. Let me put it in a different page. Okay. And that phase diagram, okay, looks very complicated, but let's look, essentially gas is mainly methane, okay, like more than 80% methane. So this diagram should give you a very good indication, even though it's not a full reservoir composition, it should give you a very good idea what happens. So here you have the pressure, okay, and this is in megapascal. If you remember, you have to multiply by 10. So this is 100 bar here. Okay, and and these are these lines that are like this. I'm going to paint one in red. This is the lines that have the same temperature. Okay, so this line here has actually 100. Okay, and this one has 50 degrees Celsius and so forth. Okay, so now let's take the point. If you remember long time ago, okay, so I hope you have a good memory. What was the pressure, the wellhead pressure for the choke that we had if we want to produce 1.5 million in this intersection? Okay, you have to believe me. The available wellhead pressure was 205 bar, yes, and the required wellhead pressure was 40 bar. Okay, was actually separator pressure. Yeah, you remember that example? Well, just trust me. That's the number. Okay, so let's locate those points here, and the temperature was around. I think was something around. Uh, the temperature was around 100, I think. Okay, I'm not exactly sure. So let's locate that point in this diagram. So first, 205 should be, you know how to read log, should be, this is 100 bar, 200 bar, 300 bar, and so forth. So we go 200, is very close to this line. Okay, and then we go up to the temperature, and the temperature is 100, so it's here. Okay, so that's the point upstream the choke. Okay, and now we have to drop to 40 bar. Okay, so let's see where 40 bar is. 40 bar is, this is 100, so this is, let me just take this one maybe. Okay, so this is 90, 80, 70, 60, 50, 40. Okay, so it's this line here, this one. Okay, and then how do I go? How is the expansion in the choke? That's something that you should be able to tell me. This thermodynamics, you have a first law of thermodynamics for open systems, yes, and it says if I have no work done in the control volume and you have no heat transfer in the control volume, the process is isenthalpic. Okay, so isenthalpic is actually the variable that I have here. This is the isenthalpic line, goes like that. Okay, and you see I got a cooling. Now you see which temperature do I have in the new point. I got a cooling from 100 almost to 60. Okay, 40 degrees it was cooled down. Okay, the fluid. Yes, so the point here to make is that you can have cooling in gas, and you say, okay, so why is that so bad? Because you can get more liquid condensation, okay, due to the more liquid condensation, okay, and you can also get, even sometimes it can be so low the temperature that you can start getting ice. Okay, if you have free water and it becomes too cold, then you start having ice, and if ice goes in the choke in these small passages, you have a blockage. Okay, so you can have free water plus low temperature, then that gives you ice block. Okay, and then another thing that you get, an unwanted consequence, so many bad things that we do just to have one intention, that is doing the first thing. Okay, but we get all of these bad things that we have to deal with. And then we have cavitation. Okay, you know what cavitation is? Yes. Okay, so the when we see on a, well, everyone has to know. Okay, not only a few. So if someone doesn't know, you have to. So the pressure, okay, when you plot the pressure, let's say that this is the x direction, okay, and then we plot the pressure here. Okay, the pressure is going to go slightly down, and then it goes down dramatically, and then it starts to recover and goes something like this. Okay, that's the behavior of the pressure, more or less. And depending on how abrupt this restriction is, how small the diameter is, this dip goes lower and lower. So what might happen is that you have, for example, you're working with liquid, and here you have the P vaporization, okay, of that liquid. So when you go down, actually here you're vaporizing liquid in the throat, okay, exactly here, and then it's going to go back to being, so here it becomes gas and here it becomes liquid again. And that process causes this cavitation that I told you about. Here I have a video. Okay, here I'm creating a bubble. Okay, for some reason the pressure in this case is giving an electrical charge, but it's having the same impact. And then when that one, if it's close to a surface and it liquefies again, then it's going to heat the surface. And after much heating, okay, that's going to happen at the throat of the choke. Okay, if you have a cage, if you have etc., at the throat of the choke, you're going to start eating the material out. Okay, it's going to start, because you have a lot. It's like having a lot of hammers working on this wall. Okay, hammering all the time, and that's going to cause again some structural problem and fail.
So we know that the problem what can we do about
What can we do? Yeah, well, live with it. That's why you have to, the choke is something you have to retrieve. Okay. You also can have erosion, especially if you have sand. Okay, erosion and with sand. But that's why the choke is not something that you leave there. You don't try to leave it there for the rest of the life. It's something that you have to think that you have to retrieve it someplace. So that's why you try to prepare everything. So you have to change it. Okay, so let's take a break, and we come back in 20 minutes. Yep. Okay, so I was telling you here that the process in the choke thermodynamically is isenthalpic, and that comes justified by this equation that you saw some time ago. Okay, that everything you have to say, all the energy that comes into the control volume, all the energy that leaves the control volume is equal to the heat exchanged by the surface of this control volume and the work transferred by this control volume, and that gives you that nice. So now let's make an experiment, okay? And this experiment we're going to say, and that's going to give us something very interesting about the choke, how the choke behaves. Okay, in this experiment we're going to put a pressure gauge, then we're going to put a choke, and then we're going to have a second gauge here, P2, and with some reason we're going to say P1 is fixed. Okay? And and we are going to start injecting a rate that we can control somehow. We have to keep the pressure and the rate we're going to change from a low value 0 all the way to something high. And we're going to see how the delta P is going, what's going to be the effect of the delta P. So initially, Qg, that let's say that that's gas, okay? P1 is fixed, and this here we're plotting delta P. So initially, if I have no flow, then I just have a delta P of 0, okay? Basically P1 is equal to P2. I have no flow. As I start increasing the rate, how that curve goes, I start having, okay, the delta P starts becoming positive, okay? P2, I have a pressure drop through this orifice, and then I have, starts getting higher, okay? All of you agree? Higher and higher and higher. But then at some point, it doesn't increase like that all the time. But at some point, I have a rate that I cannot go beyond that rate. Actually, that rate, no matter what pressure, no matter what pressure I have here, that rate will be just constant. Yes? So what's happening here? I guess you already know the answer. What's happening here is that we reached critical flow. All of you know what critical flow is? Critical flow in the throat. Okay, we reached, at this point here, we reached critical flow at the throat. And that basically is, that, for example, if we have, a piece of metal, and then okay, that's supposed to be a hand, okay, and that's metal, and you bank it, the sound or the vibration propagates almost instantaneously through that metal. Okay, so you have a velocity that transmits the change in the pressure fluctuations on that material. Okay, some velocity that at which these waves, okay, this pressure changes travel. Yeah, that's for a solid. But when you have a liquid, you have exactly the same. You have a velocity at which the pressure change travel. And that velocity is given by, is the velocity of sound, is called the velocity of sound. And in a gas, in a real gas, is given by, I think some people use C, some people use A, and you have is K R T Z over M, so molecular weight, and this K, got out of space here, this K, what is this K? Is the ratio between Cp and Cv, yes? The specific um, how do you call it? How do you call it? Forgot. Okay, coefficient at constant pressure and the specific caloric coefficient at constant volume. Okay, so that's the ratio between the two. So that's a property of the gas. So that comes given by that, and that A, for example, for K equal 1.6 for okay, R, we know what R is 8314.3. Temperature is let's say the same temperature we had before, that was 80. Okay, the temperature of the gas 73.15, and the molecular weight, let's say, is methane. This gives an A equal to around 542 meters per second. You see, it's a very high velocity. But remember what we calculated before, we already had 50 in this area. If we go to a very small area, we might very well reach around that number. Okay? And if we reach around that number, what happens, for example, when the fluid is flowing, okay, and it encounters an obstruction, immediately it propagates, so the pressure changes and immediately the pressure propagates upstream to be sure, okay, guy, I'm meeting something in front, so you have to increase the pressure automatically. Okay, and that is a process that goes at that speed, 542. But if for some reason the velocity of the gas is very close to this one, actually this pressure, this propagation, this wave doesn't have enough speed to reach upstream. Okay, so it just stays there because the flow is going on that direction and it wants to move on that direction, but it cannot because just the fluid is going too fast. Okay, so that's actually what we have that happens, this critical flow. And critical flow usually has a rule of thumb. The critical pressure ratio is P2 over P1 more or less equal to 0.5. Okay, like a rule of thumb. If you have 0.5, then you have critical flow at the throat of the choke, and then you cannot flow more than that, more than the critical rate. Then you are in critical condition. Yes? Okay, more or less what it came. Actually, it's not in gas. Okay, we are talking about a gas. Then this P2 over P1 is equal to critical is 2 over K plus 1 to the power of K minus over K. Properties of the gas. Okay, it depends on the K of the gas that I'm using. But has a good rule of thumb is if it's 0.5, that means what? If you have 40 bar and if I have, how much here? 80 or more, yes? That means I'm going to have critical flow. That means for the example we were doing before, 205 to 40, I'm probably going to have, critical flow in the choke. Yep, so I want to take this drawing and I'm going to say now a few changes. What happens if so this is for P1 fixed. So what happens if I increase P1 and repeat the same experiment? I'm going to tell you, but actually when I increase P1, you can think about it this way. You increase P1, the density is higher, right? And because the density is higher, you have more losses in this choke. So because of that, the curve is you're going to have even more pressure drop. Okay, so this is P star greater than P1, and this is P star is smaller than P1. Yes. And then we have one last thing, that if what happens with the size of the orifice, and that one is easy to see. If the orifice changes, okay, so that means for phi diameter equal to phi1, that's the choke diameter. What happens if I use a smaller diameter? How does it look like, the curve? Should it be to the left or should it be to the right? To the left. Okay, I have more pressure drop if I have a smaller orifice. That's phi star less than phi1, and this is phi star bigger than phi1. Okay, so keep that in mind because we are going to use it for our exercise. So that curve, that was for a fixed opening and that was for a fixed pressure, but when we have to select the choke, that's very important, which choke to use. So let's do now. I want to spend some time to go through the development of the choke equation, because most of choke models available in the literature, they are based on the same concept, on the same idea. I'm going to do it for first for liquid, just to show you something interesting, and then for gas, and that's going to take some time. I think up to the end of the class, but let's see. So let's say choke equation for liquid first. And that's not very, liquid, usually this velocity for liquid is extremely high. So really the fluid never reaches that velocity. So almost never we have, if we have pure liquid, we almost never have critical flow. We don't have to worry about critical flow. But if we have gas and we have a mixture, a multi-phase mixture, then we can reach very well this critical velocity. Okay, so choke equation for liquid, basically the choke, all choke models, they depart from the following, exactly from this model, where you have a big area and then you have a small area, A1, A2. And no matter the geometry, cage, needle, etc., if it's very different, all of them, because they have to assume something. Okay, they have to assume a very simple geometry. So they assume this geometry. So here, if you remember, what was the Bernoulli equation? Okay, it was dp, right? Equal. We want to start exactly with the equation that otherwise. Okay, plus 1 over 2 u squared, that's the momentum term, plus rho g dz, okay, equal to 0. I'm assuming that in this very short distance you have no frictional losses. That's an assumption, okay? The distance is short, so no friction losses. And also I'm going to say really the elevation is not an issue. Okay, this might be separated, might be inclined a bit, some millimeters, but really it's not an issue. So I'm going to get rid also of that term. And then I end up with this equation that I can integrate. So that's just the Bernoulli equation that I integrate from this position to this position. Okay. So I go and I do that. dp, sorry, here I'm missing a density of 1/2 u squared, and that's equal to 0. So I integrate both sides, 1 to 2, 1 to 2. And the nice thing about liquid, that you will see with gas, that's the whole problem. Liquid, this guy is more or less constant. Okay, doesn't change much with pressure. While for gas, that's going to be a big issue. So we take that out of the integral. We get P2 minus P1 equal to density of liquid times 0.5 times U1 squared minus U2 squared, right? Yep, you have to do some quality control. I might get some errors, but I think we are in good shape. Yes. No, actually, is it okay? Here we get U2 minus U1, so here we get, yes. I think it's okay. So now I have to express, I want to get only one velocity in this equation. Okay, the velocity, why I want the velocity? At the end I want an expression to give me the Q at standard conditions versus the delta P, right? That's the whole goal. That's the whole goal of my choke model. So I say I want to have a rate, but the rate, a very easy place to measure the rate is its upstream, okay, here, because I know that the fluid is actually occupying the whole cross section. Here is just occupying, due to this vena contracta issue, is just occupying only a fraction. Okay? So I'm going to say, making mass balance, remember all the time we use momentum balance, that was the momentum balance, and we use also mass balance. Okay, so we have this thing here, and we say actually that U2 times area 2, that will be area 2, U2, and area 1, area 1, should be equal to U1, area 1. Okay? And that means that U1 is equal to the square root of If we make it in terms of the diameter, d2 squared over d1 squared u2. Yes? And I define this is called the beta factor. Beta is called d2 over d1. And at the end, I end up with, actually I didn't have to take the root, but just u1 equal to beta, uh, beta squared, no, beta, yeah, is it, yeah, beta squared times u2 squared. That correct? No? No, let's see. This one should be like that, right? Yes or not? Now it's, okay, so now, yeah, like that, no? Yes? Are you sure? I'm not so sure. Correct? No, it's not correct. Because the area, okay, the area 1 is pi times the meter of 1 squared over 4. And area 2 is pi the meter of 2 over 4. And now I have to get the u squared. I have to square both sides. Okay, so this is true. Yes. But to get u squared, now I have to square this side and this side, right? To get u squared. That's why my equation has u squared. Okay. Yes. So I'm not so. You are more asleep than I am. Well, but it's Friday night, so it should maybe it's how do you say justified. Okay, so we're going to substitute the equation for u1 here. Okay, p2 minus p1 equal to rho of the liquid 0.5. u1 will be beta to the 4 u2 minus u2 squared. And I'm going to just say this is delta P divided by density of the liquid. Here that 0.5 is going to be a 2 up here, right? And this will be 1 minus beta to the 4, and that will be U2. Yes, U2 squared. Okay? And now we say we take the square root. Okay, we say U2 equal to the square root of delta P times 2. Did you have this derivation before? No? One of the classes, maybe fluid mechanics? No? I think you should have it some, maybe not exactly the same, but similar. And then I say, remember, I1 is the standard condition rate, okay? But I say, well, it's not so that's going to be equal to the velocity into, right, times the area of 2, right? But times also, remember, U2 is not flowing through the whole cross section, okay? But it's flowing only through a small section. So I'm going to put a multiplier that I call CD, okay? That's the flow coefficient, okay? This is called a flow coefficient or an area coefficient to account for the vena contracta, okay? Just to account that really U2 is not passing through the whole throat, but is passing through a section of the throat. Okay? Then I want to get exactly this expression, so I multiply both sides by A2 and CD. So I say Q is equal to A2 CD times the square root of delta P2 rho L 1 minus beta. And that's the expression for liquid flow through a choke. Not very useful, okay, because like I told you, we seldom have chokes only operating with liquid. But it's interesting for something else, okay, that I'm going to show you now. In adjustable chokes, then actually what happens is that the diameter of two is changing, right? And it's changing if we say, if we have, for example, this configuration. So we have here one diameter, that's what we call, for example, D2, and that's changing versus this length of this stem. Okay, if it's short, if it's long, that means that it's very, it's very actually the L we're going to define it from here. Okay, so that means if L is 0, I have no flow, and if L is completely open, that means it's fully open. It's D2. Okay, so I can regulate with this L, with this stem travel. Actually, I can regulate this area and this factor, right? Okay, so depending on the choke, I can say this is equal to a function that depends on this L times a coefficient times square root of delta P over density times 2. Okay, like you see the equation where it came from, what is the shape that I have. So this long message is just to tell you if delta P is fixed, okay, and this is L, the travel, that's like we call it the travel of the valve, okay, the travel of the stem of the valve, and this is Q. If L is 0, it's completely closed, okay, so I have no flow. And if L is 1, okay, or L, the total traveling distance of the valve, then this is open, okay. Now there is something very tricky, that some chokes, they have the following behavior with L. That means if I open 20%, I get 20% more rate. I open 60%, I get 60% more rate. 80%, I get 80% more rate. Yes, but there are some chokes that they have actually this behavior. Okay, that means that when you open a little bit, then you get a high amount of rate. You open 1%, then you get 20% rate, and then you open another 1%, and then you get 40% rate. But then after, when you are already at 80% opening, you don't get much. You have to open and open and open. Okay, and you have chokes that actually have the opposite behavior. Okay, when I open 20, 30, 40%, 60%, I almost no get no rate. But then when I start opening at the end, then I get a lot of rate. Do you see that? Yeah, that discussion, that derivation was just to show you that. So there are different. So what is the really, which choke do we want? Do we want this choke, or this choke? Okay, we want that when we change, it will be really accurate. That really, when we change 20 to 30 to 40%, we get exactly a big change in pressure drop. So we want a mixture of this choke, and we want a mixture of this choke, both of them built into one. And still people trying to find it, trying to do some magic to make it. But just be aware that you, depending on the choke that you have, you might have this type, and this type. And usually the manufacturer tells you which type of choke you have. Okay? But that's because we cannot do that for gas. It's becoming, it's going to become a mess. So I wanted to show it for liquid. Okay, liquid is not so used. The equation looks like that. But here it's nice that you see that the area of 2 and this beta factor, they depend on the opening. And they depend on the position of the valve. And I have different behavior for that. Okay, now let's go for the case of gas. And here we're going to have fun. It's going to be exactly the same procedure, integrating the same equation, but now the density it has to change. So dP plus 1.5 density velocity squared. Okay, let's call it U to avoid confusion with volume. That's going to be equal to 0. So then I integrate from 1 to 2. So let's make here put a title for gas. Okay, and basically this is also the orifice equation. Okay, because we are assuming that you're looking only at this part. So really, if this is very short, this equation is also good for a very short orifice. We are assuming in this development that after this point, basically the pressure keeps the same. You have no recovery of pressure after that point. That's the main assumption of this model. And you can try to improve it, but that's the main assumption. Okay, so here I get the same thing. No, I don't get the same. Okay, I prefer, I prefer to take this away and put the density here. Yeah. Okay, you agree? Just to keep it properties with properties and velocity with velocity. So here I get exactly the same, that the integral from 1 to 2 dp over density is equal to 0.5 u1 minus u2. So here comes a very nice assumption. I can say in a gas, okay, usually u2 is going to be much bigger than u1. So in that respect, u2 squared is going to be also much bigger than u1. Okay, so u2 minus u1 can be approximate to u2 squared, and I get rid of the u1 from there. I don't have to do mass balance, etc. I just got rid of it because I say the orifice is going to be so small that I'm going to have a very high velocity there. That's one assumption. Then the other assumption I make is that the density is equal to, if you remember, from the real gas equation is P over Z R molecular weight and T, right? So I can use that equation for the density. But also we know something else. We have all of these choke models. So this is the momentum equation for this is the momentum equation for the gas. And also I have to make some assumptions. So I know the gas will pass through a process from 1 to 2. Again, I have to make an assumption about that process. And that's where it comes the difference in many choke models, the type of process that I assume. So normally, a process that is possible to assume is adiabatic. Okay? And in an adiabatic process, you say that it's like a polytropic process, P over 1 over rho, but now the exponent is to the k, and then you say this is constant. Okay? You remember the polytropic process, P times V to the n is constant? Okay? But if you are adiabatic, then n is exactly equal to k, to the ratio between the specific heat of at constant pressure and at constant volume. Yes?
You get the integration of 1 per 2 u squared, velocity squared.
Here?
Yes.
Yeah, well, this is your what do you say?
I think get what the result of this integration.
It's just evaluating all of this in 2 minus all of that in 1. Okay? You're integrating along the flow, so in the direction of the flow.
Okay.
Okay? So you have actually no differential there. Yes? More or less. Let's see where did we have the original equation? Yep, I can find a better way to explain it, but let me follow with the, okay, let's assume that's correct and that gives you that, and let's follow the discussion, okay? And then I will try to find another way to explain the equation. Okay, so we have this process that is constant, and then we can say, then we can substitute actually that density by pressure, right? And we can make an integration. So you can say that the density is equal to this constant that I call C divided by P to the 1 over K, right? Here you have to be careful, you have to check me because I might do a mistake. Actually, it's the opposite. Pressure over C. Okay, and then I substitute this expression into my integral, and then I obtain integral of dp over p, and here I have c to the 1 over k, p1 over k, from 1 to 2, and that gives me actually k over k minus 1, p 2 k minus 1 over k minus p1 k minus 1 over k, and c 1 over k, if I didn't make any mistake. Then I know that c, then I take p1 as a constant, p1 k minus 1 over k, p2 over p1 k minus 1 over k minus 1, and this p2 over p1 I call it y, k minus 1, c to the 1 over k, and then let's see what else. There was another trick that I had to make here. Then these two, they can this is actually density pressure over density. Okay, these two, and the justification of that is that c 1 over k, that's equal to p 1 over k over density 1. Yes. Okay, and then I substitute that here, and then I obtain the expression that this gives me p1 over density 1 k minus 1 over k, and y to the power of k minus 1 over k minus 1. Okay, and that was u2 squared. Okay, actually here was minus, right? Because it was u1 minus u2. Yes or no? Okay, I'm getting tired, and you're also getting tired. Yes? So what have we done so far? We had the momentum equation. We substitute, we said, is a adiabatic process. That gives me a relationship between pressure and density, and that's very convenient because I had actually pressure and density in the same integral. Okay? And then I integrate using some heavy math, okay, some mathematics, and then I finally end up with this equation that is almost what I want, okay, but I have to get rid of this density. I have to, I have the equation of state to get, so I have to get rid of two things first. I have to get rid of this u, okay, because I want at the end is the standard conditions rate. I don't want u, and I'm going to do the same trick that we did for liquid, and I want to get rid of this density to put it in terms of pressure. So here is where I use this p1, density 1 is equal to p1 molecular weight r Z1 T1, right? I'm going to substitute that here, and then it's nice because I have pressure, and pressure is also here, so I can group them together. So I say U2 is equal to the square root of all of that, 2P1 over P1 molecular weight R C1 T1 K minus 1 over K yk minus 1 over k minus 1. So then this one goes away. I think I made a mistake here someplace. Okay, yeah, I changed. I'm not sure why I changed, but this should be k over k minus 1. You're not paying attention, and I'm not also paying attention. Yes? So I have said, I have T1, I have K, which is a constant, and I have this relationship of pressure. So now I say, how do you define U2? U2 is defined as some rate, okay? Or I can define it actually better, not to define it with rate, but I can say this is the mass flow divided by the density of 2 times the CD times the area of 2, right? Because really the velocity, okay, it's passing not through the whole area of 2, but it's actually passing only through the throat, okay? And then after I have that, but I have one bad thing, which is I have the density of this guy here, but I know that P times density to the K is equal to a constant. That means that P1 density 1K is equal to P2 density 2K. And that gives me then that density of 2 is equal to P1 over P2 times the density of 1 over K. Yes? And then I have, again, to substitute here, I have to substitute this expression that I'm going to copy. Okay, so I'm going to substitute that expression also here, and then I substitute that into the equation, and I'm not going to do the whole derivation because there is a lot of things that I have to make, but at the end, I end up with this equation. Of course, and remember that the mass flow, okay, is also equal to the Q at standard conditions times the density at standard conditions, right? And the density at standard conditions is P times M over P standard conditions, T standard conditions, Z is equal to 1, and here you have R, okay? So also you substitute that into that equation. Okay, and you end up with this equation that tells you that's only for when the flow is not critical. Okay, when the flow is critical, remember it's just a function. So if y is it's above y critical, that remember this is around 0.5, then I just use this equation. Okay, then I just use this equation. But if y is less equal than y critical, then use this equation with um, y equal to yc. Okay, because you're not going to get more rate. It's not that if you change, you start reducing the pressure. Okay, is 0.8, 0.5, and then when you reach 0.3, remember the rate goes up like that. It's a vertical line. So no matter how you lower the pressure, you will always get the same rate. So that's why it's the same as evaluating this expression at y critical. Okay, so that's the equation we're going to use, and let's see if we can make an exercise to wake you up and see how much did you get. But basically, there is something very interesting that this area 2 is pi times the diameter over 4, and this is the diameter of the throat of the choke, and basically it's the diameter of the bean choke that I have to use. Yes? Okay? So, so that means, for our application, we're going to make now an exercise. So that's just to show you the equation, where it came from. And we're going to make an exercise based on, the Excel sheet that you have, that I say I performed, or you performed, actually some days ago, was 2 days ago, the WPR versus P separator, okay, equilibrium. You perform these two curves. Okay? And then you said, I want to produce 1.5 e to the 6 standard cubic meters per day, and I need this pressure delta P of the choke. Okay, and this one was PWH available was 205 bar around, and PWH required was 40 bar. Okay, so that gives you a delta P of the choke of 155, right? Okay, so I'm going to say, using that equation, now you have, that's what you need. Okay, using that what you need, and using this equation, please calculate the diameter of the choke that you need to have exactly that pressure drop. Okay, so please open your the Excel sheet that I gave you, the second one. Okay, it's called choke performance dry gas. And you don't have to worry about this ugly equation. I already programmed for you. But I feel obliged that I have to show you how it was derived, because all choke models are the same. Momentum equation between inlet and throat, and also you have to assume that the gas or the fluid is passing through a thermodynamic process from 1 to 2. And then you try to simplify. Okay, but they're always based on the same. Okay, so you open that equation and you got this one. Okay, you say that's the discharge coefficient that we're using in the equation. The choke temperature, that's T1. The critical ratio, you see, is very close. That's this equation that I showed you before. Okay, I told you it's 0.5, but actually it's not 0.5. Is this equation, okay? 2 over k over k minus 1. So that tells you it's 0.546, which practically is 0.5. Temperature, specific gravity, everything you need. But here you have what you really need. So you have the upstream pressure, the downstream pressure. How much is that if we divide these two? Is it more than 0.5 or less than 0.5? This one divided by this one, okay, 195. So I should have critical flow. Yes? Okay. So see here I have all the properties I need. That's the Y I have. That's the pressure, inlet pressure, and the set. That those are things that I need. Let me put it side to side with my equation. Where is that? So, okay. So those are all the things that I need for my equation. Um, I need C1. I need the temperature of the choke at the inlet. I need these standard conditions that they are given here. I need this coefficient, and I need also, here is the diameter of the choke. Okay, have it in millimeters. This is like how much is that? Half an inch, right? So I have a choke of half an inch. And if I use that choke, and if I use that equation of the choke, I get a rate of, that's that equation. That equation is programmed here, Alt F11. The equation is coefficient rate metric. Okay, that has that ugly equation with all the input that you have. So that gives me 446 e to the 3. And remember how much I wanted? Do you remember? I wanted 1.5, right? 1.5 e to the 6. Okay, and I'm getting, for that pressure, upstream, downstream pressure, And for everything else, I'm getting 446. So what to do? I told you, 3 days ago that we could use something. It's like to having a very efficient brother, little sister that they can do. Okay, the solver. What are we going to tell the solver? Change. What can you change? Can you change the inlet conditions? No, that comes from the well, from the reservoir. Okay. Can you change? Yeah. Can you change temperature? No. Can you change downstream conditions? No. You have the separator pressure. That doesn't. You cannot change it. Okay. So the only thing you can change in that equation is the diameter of the choke. Okay. You can go and change and put another different choke. So that one is here. Okay. 12.5. So what I'm going to say is, say solver, please change this number until I get here exactly 1.5. Okay, so let's try it. Okay, I want to change this number. I want it to be exactly equal to my production rate, 1.5 e to the 6. And I want to change, the only thing I can change in this choke is the diameter. Okay, the D2, which is here, choke diameter. Okay, then I run it and it found it. But let's see what diameter do I get. 22.9, that's like 1 inch, okay, choke that I need to put on this well. All of you got the same? Yes? Okay. And of course, I'm operating, I ask you, am I operating in the critical region or in the subcritical region? Do I have critical flow in the choke or not? You go to data, you go to solver, and then you say, I want to change this rate to be equal to 1.5, and by changing the orifice size. Okay, and you see we got, instead of getting half an inch, we had to go for an inch choke to get exactly that rate. And you see the ratio is zero point 0.2, okay, that I'm having from 205 to 40. That means I'm below 0.5. That means I have critical flow in this choke. Okay, I have it. Okay, so now I ask you, let's go to this diagram. I think it's a bit useful to say QG and delta P, okay? And I have this series of plots, okay? That is for 1P, 1 fixed. And we have this plot, and this plot, okay? And we have a point here that we say this is 1.5 e to the minus 6, and the delta P is 155 bar, okay? So that's actually what we are doing with this equation. We are trying to find, okay, we have multiple curves, okay? For example, the one that gave me 22, okay, the one that was initially half an inch, 0.5 inch, that one was here. That one will give me a different rate, a much lower rate, 400 e to the 3. If I use a bigger rate, I was going to get a higher rate, okay? Like for example, 2-inch choke will give me a higher rate. So I have to put the curve exactly where it gives me exactly what I require. Yes? Okay? Like I want exactly one choke, so the choke of exactly 22.9 millimeters, this is the choke of 22.9 millimeters, that passes exactly to that rate that I need, okay, in critical. Please be aware that also the point, in this case the point was here, but also the point might be here. Okay, might be in the critical region or might be in the subcritical region. More or less clear? Yeah, well, so, a choke is a bit heavy. We can refresh it on Monday, but huh?
How to use source to get 1.5.
You say first, remember what you want.
Yes.
What you want? What do you want?
You want to
To
find,
finish early? What do you want?
you want to find the rate of
Yes, you want this value. That's your objective. Okay, that's the value you want to be 1.5.
yes.
Okay, million. And then you put here how much you want it to be.
Yes.
Okay, and then what are you going to change? This diameter here. That's the only thing you can change. All the rest you cannot. You cannot change downstream pressure. You cannot change the upstream pressure. Okay, and then you just click go. Very simple. Solver makes your life simple. Okay. We have to all the time when you open the solver, you have to say what what is my objective? What do I want? So you detect that cell first, and then you say how what I'm going to change, to give me what I want. What do I have to change? Okay, these two cells are the only two that you need in the solver. Hmm? Okay, so let's wrap up. Unless you have any question. Okay. So let's say let's put this homework so you can practice. Okay, so using the same data, so this is homework, so you can remember, I think the learning doesn't happen because you're sitting here listening to what I say. That's partly helps. But the learning happens when you actually go and do things. That helps to consolidate the knowledge that you received in class. Okay, so that part is extremely important, and I think you should. That's why we have. It's not because it's nice or because we like it. It's because it helps you to fix the knowledge in the brain. Okay, so using the same data shown before, okay, or used before, that means P1 equal to 205 bar, P2 equal to 40 bar, and the diameter of the orifice equal to 22.9 millimeter. Okay, make the following plot. Okay, you have to make a plot of delta P versus QG, okay, with P1 e constant. And for that, you will have to destroy a bit the sheet. You have to find a clever way how to do it. Okay, but you have to generate this one. Okay, and the way I suggest to do it is that, let me take that sheet here. You have somehow to change that pressure. Okay, this pressure, it has to be a variable because that one is fixed, and the only way you can get different delta p's is to change p2. Okay, so you have to put it here in this column. Okay, the downstream pressure, and here you're going to get a delta p, and that's going to be this number minus this number. And then you change this pressure from a very, very close to 205. It will give you 0 rate. And then you start, and for all the rows below, you're going to put 205, and then you're going to reduce it all the way to 0, okay, to see how the curve looks like, to generate this curve with delta P versus rate. Okay, that's my suggestion. You can do anything you want. You can do it everything from scratch. But what I say, now this one becomes a variable. Because P1, I'm saying here, I want P1 is constant. It has to be 205. So to generate this plot, you have to change actually the P2. Okay, and I say 205 might be 200, then I go 170 and so forth all the way to 0. Okay, that gives you a different delta P. One which should be constant. Okay, and that gives from delta P0 to delta P 205, and you should get exactly this behavior. Okay, so that's the homework. Yeah. So let's wrap up to see what we have done today. Was heavy day with choke. Choke is not easy, but so first we said we went to one application why we want to calculate pressure along the tubing. Again, one of them is to find the velocity of the phase in the tubing. And to find the velocity, we had to say, well, we want to calculate this BG, and we want to calculate the local rate. And after we have the local rate, we can calculate the, this is not standard condition, but this is local at PNT. Okay. Then we said, let's use that, we already have the velocity. So let's use, what Milan taught us was on Wednesdays to say, to calculate the erosional velocity and the liquid loading velocity and see how our velocity is compared to them. And we saw this well has a problem. Okay, has too high velocity, so is violating this erosional velocity. Okay. Just to show the example why it is important to have the pressure along the tube. Then we talked about choke, and we talked about general things about choke. Positive choke is fixed and it comes in different diameters. It's something that I can change and remove. I have to do it manually, say send someone to the field. So usually it's not very suitable for subsea wells. And then we went to this adjustable to see how they look like. But I told you, all choke models basically they go down to this basic model. Okay, you have something, an area very big, and then you go through an area very small. And almost all models are derived based on that. Only a few are not. So I told you problems that you have, cooling, erosion, cavitation, etc. we cannot avoid. And then we started to say the thing with the choke is that there is a maximum rate that you can reach through the choke. If the inlet pressure is fixed, you have a maximum rate that you can reach through the choke. And this is called critical. This happens when at the throat you reach the critical speed. Okay, and we say that's around 500 for gas. And then we went to the derivation, was heavy. We did it first with liquid, and we said basically that you have a coefficient that depends on the diameter of the throat, and if you change if you have something, so if you have a proportional relationship, then you have a proportional relationship with the rate. That means if I have 20% opening and get 20% more rate. Okay, but I can have chokes with different behavior. And then we went to the full derivation with gas, which is very heavy. Okay, basically momentum equation between 1 and 2. Also, I have to assume adiabatic process between 1 and 2, substitute all of that inside the equation, and then at the end I have to substitute that actually I'm not flowing through the whole throat, but I'm flowing through an area of the throat. Okay, and that's why I use this CD coefficient. We got the equation. I don't expect you to really program it. I think that's I think too much. We will spend a few days just that which units should I use, program it, etc. So I say just use that Excel sheet that I gave you, and we did this exercise in class. So I hope that you now go and practice it with this homework that you have for today. Okay. Before we finish, any questions? No. Okay. So see you on Monday. Enjoy the weekend.